In this video, we're going to do a quick review of writing chemical equations. Remember, chemical equations are just a summary of what's happening in a reaction. Rather than write big paragraphs, you can write it in this format over here, where you have an arrow over here. This arrow means to produce or to yield or to make. On the left side of the arrow, you have the reactants. That's what you start off with. And on the right side of the arrow, you have the products or product. That's what's made. So the way you can read this is nitrogen reacts with, that's what the plus means there, reacts with hydrogen to produce or to yield or to make ammonia, NH3, which is the product. This arrow does not mean equals because these are not equal to this. They're different overall. They're different. So the arrow really means to produce or to make. You can also, in a reaction, write the states. The states are either gas, liquid, solid, or aqueous. Generally, you'll be told the states, but there are some you'll kind of need to know. So, for example, the Hofbrinkel, as we saw in the previous video, we know what the states of those are. Metals are usually solid at room temperature. When I say solution, that usually means aqueous because it's something dissolved. So we say aqueous dissolved in water. The aqua part means watery, so watery solution. And those are all some basics that you need to remember for writing equations. Remember, there's different types of equations that you can write. You can write what's called a word equation. You can write a skeleton equation, and you can write a balanced equation. The word equation represents the reactants and products using their names, so their actual words. We don't put states or anything. We still use the plus and the arrows, but we just don't put any formulas or states. So let's look at this description here. When aqueous beryllium chloride reacts with aqueous silver nitrate, it produces aqueous beryllium nitrate and silver chloride powder as a solid. So what we have to do is identify the reactants first. So you can see here what's reacting. Beryllium chloride reacts with silver nitrate. So those are my reactants. We have beryllium chloride plus silver nitrate because they're reacting together. And they're going to produce, so we're going to put our arrow there. On the right side, we're going to put the products. So what is made? Well, we have beryllium nitrate. That's one product, and silver chloride. So I put a plus to separate the two products from each other and put the other one here, silver chloride. That's a word equation. Word equations are not always the most efficient to write because you have to spell all those words out. They're not very universal because right now we're writing this in English, but different elements and compounds have different names, whether you're speaking English or Italian or French or other languages. Not everyone gets them. So to be more universal, what you can do is you can write these in their formula format. And so all we do is we do the crisscross rules or the rules with the prefix, depending on what type of compound you have, to convert them to their formula. So beryllium chloride is this. Keep the plus where it is. Silver nitrate is this, so that was crisscross. Put your arrow, keep the arrow where it is. Beryllium nitrate is this by crisscross, and silver chloride is this by crisscross. And because in the equation or in the description we told you the states, you could put the states in as well. So aqueous for beryllium chloride, silver nitrate was also aqueous, that's a solution. You can put AQ. Beryllium nitrate, also aqueous. You can put AQ next to it. And I'm going to write this out in a better format later on, but just showing you the idea. And then for silver chloride, it's a solid, so you can put solid next to it over here. So that's called the skeleton equation. That's called the skeleton equation because it's not balanced. If you notice, and you look at this carefully, you'll see that the atoms don't match up on both sides. Here you have one beryllium. Here you have one beryllium. Here you have one silver. Here you have one silver. Those match up. Here you have one nitrate. Here you have two nitrates. That doesn't match up. Here you have two chlorines. Here you have 1 chlorine. That doesn't match up either. So a skeleton equation doesn't really care about being balanced. It doesn't care about following the law of conservation of mass. It's just a quick way to write the general idea of what's happening. But in reality, reactions happen in a balanced form. So when you're done writing a skeleton equation, you can go and try to balance the equation out by putting coefficients in order to have the equal number of atoms of each type on both sides. And we'll review that as we do some examples together. The balanced equation as well will have the states written next to it if they're provided, or if you know enough, you can put the states next to each of these. So just to summarize there, we saw that equations can be written in a word equation, a skeleton equation, and balanced equation. Typically, whatever I ask you for, I recommend you start off with the word equation, so that way you can pull all the necessary pieces of information out of the description over here. And then after you have the word equation, then all you have to do is convert them to the skeleton equation by doing crisscross or rules for molecular compounds if they're molecular. And then after that, all you need to do is balance. So that's kind of the progression you should take: word to skeleton to balanced, and then you'll make fewer mistakes if you do that. So let's do an example here together. When dissolved, aqueous sodium hydroxide reacts with sulfuric acid. It produces aqueous sodium sulfate, water, and heat. So we'll start off by writing a word equation. So we have sodium hydroxide reacting with sulfuric acid. So sodium, we don't put any states in the word equation. Sodium hydroxide reacts with sulfuric acid to produce, it says sodium sulfate, aqueous, but you don't write aqueous here yet. Sodium sulfate plus water. And there's also heat generated, so people will write energy or heat here. That doesn't really affect anything in the skeleton equation very much, or in the balanced equation later, so no big deal. So here we have our word equation written out. Now I want to convert it to a skeleton equation. And so we're just going to go one reactant and product at a time and convert them to their formulas. So sodium hydroxide, okay. We have Na plus 1, OH minus 1. You crisscross and you get NaOH, because it's 1 and 1, and you don't need brackets around the polyatomic ion when you have the 1 there. And it's aqueous sodium hydroxide. It's dissolved. So we can put AQ there, plus sulfuric acid. We didn't learn how to write formulas for acids yet, but later on you will. Sulfuric acid, just to give you that one, is H2SO4. And typically acids are also solutions, so we'll put aqueous. And then that will make sodium sulfate. So sodium sulfate, we have Na plus 1. Sulfate is SO4 minus 2. Crisscross it, and you get Na2SO4 AQ, because it says it's aqueous sodium sulfate, plus water. And you know what water is, H2O. Generally, the water in these reactions are going to be liquid, unless I tell you otherwise. And then plus heat. So that there is our skeleton equation. We don't care if it's balanced at the moment. We just wrote the skeleton equation out. The next step is writing the balanced equation, so we can do that. What I typically do for the balanced equation, maybe you have a different strategy than I do. You can use your strategy instead. I just like to count atoms on both sides and then just add coefficients until everything sort of equals on left and right side. So on the left side, I have 1 sodium. On the right side, I have 2 sodiums. So right away, I know I'm not balanced. In terms of the sulfates, I have 1 sulfate group here and 1 sulfate group over here. So that balances out. I'm going to show you a quick trick that might help you balance in situations like this. I'm going to rewrite water as HOH. You don't have to do this. You can just count the water as H2O. But if I do this, then here's what it allows me to do. I have one hydroxide, one hydroxide. And then I can treat the H sort of separately. So this is one H here, two H's here. So I'm going to choose to try to balance something here. I'm going to try to balance the sodiums first. So I have two sodiums over here. I'm going to try to make two sodiums here by putting a 2 over here. When I do that, that multiplies everything by 2. So this is now 2 sodiums, 2 hydroxides. So my sodiums are good now. Sodiums are balanced, but my hydroxides aren't. I have one hydroxide here, but 2 here. So I'm going to put a 2 over here. When I do that, that gives me 2 H's and 2 hydroxides. So what you'll notice is now my hydroxides are balanced. And look, my H's are also balanced. And my sulfate's already balanced. So now I've written a balanced equation. Okay, so just to rewrite that here, we have 2 NaOH AQ plus H2SO4 AQ produces Na2SO4 AQ plus 2H2O liquid plus heat. In reality, you wouldn't need to balance the skeleton equation unless I tell you to. So if I tell you write a balanced equation, start off by doing the word, then do the skeleton, then go ahead and balance it. So that is a quick review of how to write skeleton, word, and balanced equations. We'll try another one. I recommend you pause the video, try it yourself, and then check your work after to see if you're on the right track. So here we have when fluorine gas mixes with calcium metal at high temperatures, it creates calcium fluoride powder. So let's go ahead and write that out. Remember, word equations, they don't have any states in them. So we just put fluorine reacts with calcium and it produces is the same thing as produces or makes calcium fluoride. And you don't have to put powder. That just tells us that a powder is in the form of a solid. For later on, we can write that out. Calcium fluoride. So we're going to convert this to a skeleton equation by writing everything as symbols, formulas. So fluorine, remember, is one of those Hofbrinkels. So you need to write F2. And we know it's a gas because it says so over here, but also fluorine is gas as a Hofbrinkel. Calcium, it's not a Hofbrinkel, it's simply Ca. Metals are usually solid at the temperatures we react them at, so calcium is solid here. And just remember that if you have a metal, unless I tell you otherwise, it's going to be a solid. And then we have calcium fluoride created as a solid here as well, a powder. To find that, I just do the crisscross between calcium and fluorine, and these charges are just from your periodic table. Fluorine's -1, calcium's +2. We get CaF2 solid. And so that is our skeleton equation. Next, we'd have to go and balance the equation. So again, I'm just going to start by counting some atoms on both sides to see if we're on the right track here. So here I have 2 fluorines. Here I have 2 fluorines. Here I have 1 calcium. Here I have 1 calcium. It looks like everything is already balanced. See, the nice thing about counting first is that sometimes your equation is already balanced, so you don't have to do a lot of work. You just count. If it's already balanced, you're done. So just to rewrite it here, it's already balanced. F2 gas plus Ca solid. They're reacting to produce some calcium fluoride. All right. So we'll try the next one here. So this next description is given to you. Pause the video, try it yourself, and then afterwards unpause the video to see if you're on the right track. Give yourself some feedback, assess yourself, and make sure you correct the mistakes you made. Sodium metal reacts with iron 2 chloride, and when it does that, it forms iron metal and sodium chloride. So when sodium metal reacts with iron 2 chloride, it forms iron metal and sodium chloride. So Let's write out the reactants first. So the things that are reacting are sodium and iron 2 chloride. And they're going to produce or form iron and sodium chloride. There's our word equation. We can go ahead and try to write this as a skeleton equation now by writing everything as symbols. So sodium is a metal, so that means it's usually going to be a solid at room temperature, so NaS, plus iron 2 chloride. So here, iron is +2, chloride is -1, crisscross, we get FeCl2. Now, we didn't really tell you the states here, so I wouldn't expect you to know these. But generally, in these type of reactions, when you have a metal reacting with some compound, it's usually going to be the compound is aqueous. It's going to be dissolved in water, just because the ions can move around more, react more efficiently. So that's going to make iron, so iron metal, just Fe. No need to put iron 2 here. So the reason we have iron 2 here is because in the compound, it's in the form of an ion, right? It actually exists as 2 plus and minus here. But when it's in the form of a metal, it's no longer an ion. So it's just iron solid. You're only really putting, you're never really even putting this Roman numeral anywhere other than in the word equation. Okay, nowhere else. Okay, so iron plus sodium chloride is Na plus Cl minus. Crisscross, you get NaCl, and usually the compound that forms there is also going to still be dissolved in water, aqueous. So now your next step is to balance the equation. So we have one sodium, those look happy, one iron, those look happy, but unfortunately, the chlorine is making our lives difficult and is not very happy. So we have 2 chlorines on the left side, and we have 1 chlorine on the right side. So we need to kind of figure out what we got to do here to balance this out. So we need 2 chlorines here. So simplest thing is to just put a 2 here. That makes 2 sodiums, 2 chlorines. So chlorines are happy, okay? But now your sodium's not happy because you have 2 sodiums now. So let's just go make that happy. Let's put a 2 here. So 2 times 1 is 2. So now my sodiums are happy, and my irons were already happy to begin with. So now it looks like everything's balanced. So we have a balanced equation. We have 2 sodiums react with the 1 FeCl2 to produce 1 Fe plus 2 NaCl AQ. Generally, you don't have to put the ones, but as when I start learning this, when someone starts learning, I just recommend they put a coefficient of 1, just so they know that they've actually balanced it and they get into the habit of putting coefficients down. But just realize that if there's no coefficient, it really means that there's just a 1 in the front. Okay, otherwise we wouldn't write it down if there was none there. Okay, so generally coefficients of 1 are not needed, but just for practice, you can put 1s down to show that you're fully done balancing the reaction. So what we saw there was, again, how to write word equations, skeleton equations, and balanced equations. In the next video, you're going to take a look at how to identify reactions based on their type. Since you've already seen that, we can just quickly do an overview of that, see if what you might know. So if I were to ask you this one over here, what type of reaction is it? Is it synthesis, decomposition, single displacement, double displacement, or combustion? You can try it yourself. If you don't know this one, don't worry. You'll go in the next video and you'll try it out. You'll learn about it and you can come back to identify them. This here would be a single displacement reaction, SD, single displacement reaction. Here, same idea, synthesis, decomposition, single, double, or combustion. 2 things coming together to make 1. That's a synthesis reaction. Here, it looks like this switched spots with this. So we have a double displacement reaction, more specifically called a neutralization. And over here, also a double displacement reaction, because these 2 things switch spots. They switch partners. No one's alone in the end, so double displacement reaction. Again, if you were not too sure of that, you'll see that in the next video where you get to review the types of reactions. And please make sure you review your types of reactions videos as well as you're studying word equations, skeleton equations, and balance equations, because it's a great way to study all the concepts all together.